So thank you, sir, for giving me the opportunity to present today's tutorial. Good afternoon, everyone. Myself. Myself, Jagrita Pal, a research scholar from the Department of Computer Science and Engineering, Tripura University. So today my topic will be hands-on practice using the microscopic images to classify normal and abnormal precancerous cells with sequential convolutional neural network. Proceeding towards my first slide. So these are the contents which I have included in my presentation today. So first of all, in the introduction part, I'll be like giving a little explanation about what is cell and what is the need to do image classification, what is its importance, and what is the need for microscopic image classification also. Although it has been explained earlier, so I'll be giving just a few concepts about that. And then what are the different types of image classification and what datasets I'll be using for microscopic image classification. That is two datasets, AGMC2 dataset and high-level dataset. And the model which I'll be using for image classification is VGG16. And why I have used particularly VGG16 for image classification, I'll be also explaining that what are the basics of VGG16 and that also the diagrammatic representation of microscopic cell image classification on AGMC2 dataset. And what are the data augmentation techniques and the Python code running platform for AGMC2 dataset as well as the high-level dataset, because I'll be explaining about the two datasets. So yeah, and then conclusion and references. So this is my introduction, like what is a cell? As you already know, cell is the basic unit of life, I guess. So a cell is the structural and functional and biological unit of an organism. Cells are the basic building blocks, and human bodies are composed of cells, as Madam already, Professor Niharika Nath Madam already explained what is cell, and you all know about that. So I just kept a basic concept what is cell. Every cell is composed of plasma membrane, cytoplasm, nucleus, and a nucleus or whatever. And in eukaryotic cells, it is known as nucleus, and in nuclear in prokaryotic cells. So basically, I'll be performing image classification, that is microscopic image classification in cells. So what is the need for image classification? Image classification is a fundamental task in computer vision, which involves assigning a particular category or label to an entire image based on visual content. Like there are various class levels in an image. If we want to classify each class level in different way, then we need image classification to enable computer see and understand images by assigning them to predefined categories. Like I have taken an example here where example in that example, like there are various figures like a cat, dog, and a frog. And if we train the model, like it is a supervised learning technique where we will be giving the labels as well as the images to the model to train them so that it can classify which one particularly describes which part. So here, the model after training the model, it clearly classifies which one is dog and cat. It is just an image, nothing else. Classification of an image using machine learning. Proceeding towards next slide. Why do we need microscopic image cell image classification? So basically, I'll be doing microscopic cell image classification using a deep learning neural network. So why should we do that? The need for microscopic cell image classification arises from its crucial role in automating cell-based analysis for applications like disease diagnosis, drug screening, and genetic research. Generally, microscopic image classification plays a vital role in biomedical research and allows models to automatically analyze several cells textures and patterns. Traditionally, this process is done under a microscope. So it is a technical issue. I'll be continuing from that part. Depending on the problem at hand, there are different types of image classification methodologies that need to be employed. So the datasets I have taken is a GMC2 dataset and high-level dataset, which I have told in the content part. So these are generally binary classification dataset and multi-class classification datasets. What is binary classification generally? Binary classification takes an either logic or two-level images and classifies unknown data points to two categories. Like when our task is to categorize benign and malignant tumors, analyze product quality to find out whether it has defects or not, and many other problems that require yes or no answers are solved with binary classification. For example, if we take a dataset that is the dataset which I'll be working on a GMC2 dataset, that is a binary class dataset. So in binary class dataset, there are generally two classes. That is the dataset which I'll be working on has two classes: abnormal and normal cancerous cells and normal cancerous cells. So when there are two classes from a dataset, that time we can use binary classification tools. In case of multi-class, that is more than two classes, we can use multi-class classification tools. In case of multi-class, that is more than two classes in a dataset, that time we can call it as a multi. I will be working on from next slide. So the network is a bit disturbing today. So I'll be continuing from this part. Here you can see that there are three classes which are classified as multi-class classification. Basically, machine looks at the features, like how is it classified how is it classified in different way. Basically, the machine looks at the features like what is that shape, color, texture. So while the model is being passed through neural networks, so the machine generally identifies the particular shape, color, or texture and chooses in which class the picture is most likely to be based on the training it received. Proceeding towards next slide. What are the datasets I took for microscopic image classification? Here we'll be performing image classification for microscopic data, where basically we consider two datasets. As I've already mentioned in the content part, I'll be taking the AGMC2 dataset and the HighLev dataset. For AGMC2 dataset, it is a binary class dataset where there consist of two classes, that is abnormal image, abnormal cancerous cells and normal cancerous cells. So I'll be training my VGG16 model on that data so that it can classify the cancerous cells as abnormal and normal correctly. So for the AGMC2 dataset, a binary classification task is performed since it contains two categories of cell images. In contrast, the HighLev dataset is a multi-class classification task. It comprises of 7 distinct classes of cervical cell images. In HighLev dataset, the class consists of 7 distinct class features, like there are 7 different class categories. So I'll be performing I'll be training my model on HighLev dataset too, so that it classifies particularly an image belongs to which particular class. In this project, I have utilized the VGG16, which is a deep learning model for microscopic cell image classification. So why I have taken VGG16? VGG16 is a convolutional neural network, that is CNN architecture, which is specifically designed for and widely used in image classification tasks. It is one of the popular algorithms for image classification and is also easy to use. There are various other classification architectures. There are various other classification architectures also. But the main reason why I chose VGG16 is that it offers really a good balance between accuracy, simplicity, and computational efficiency. Since VGG16 has slightly fewer layers as compared to other classification architectures, so it almost equally trains faster, especially on smaller datasets. It is also a much less complex model as compared to other algorithms or other neural network architectures, so I've preferred VGG16 over my dataset. For my dataset and experimental setup, VGG16 provided excellent performance with less complexity. We have used the supervised learning technique here, where I'll be giving, as you all know what is supervised learning technique, we'll be training the model by giving the input images as well as the levels, we'll be passing the input images to the VGG16 model neural network architecture, so as the model to learn about the features, about the shapes and textures. We have used the supervised learning technique here using the pre-trained model weights of VGG16. Overall, VGG16 was the most practical and efficient choice, offering high accuracy with simpler implementation and faster training time. So we'll be explaining about the VG16 model from the next slide onwards. But to understand the basic concepts of VG16, we need to understand about what is CNN, like what is convolutional neural network. I just given a few topics about that. Like here I have taken an image. So this is just a small part of that image, which is also can be called as a patch. So and generally an image consists of pixel values. Like if we make it enlarge it, then it considers of just numerous numbers, numeric values. Imagine you have a photo and you can tell it's a cat, but how can a computer recognize it? A computer only sees a grid of numbers, that is the pixel values. What the computer sees, that is, after training the model, it can classify as what is it and what is not. So we build a model that can learn to see shapes, edges, textures, just like our eyes, and we can say that as convolutional neural network. Here the image is three-dimensional arrays of integers ranging from 0 to 255. As you all know, the pixel values come from 0 to 255 and of size, width, height, and 3. Here the 3 represents the RGB, that is red, green, and blue, 3 color channels. So it's just an image, nothing else. That is training a model about classification, like what are they giving different levels and training it, which are called oranges and what are called apples. So if we give the input as that, so it can easily classify that there are 2 apples in the picture. VGG16 is one of the most famous convolutional neural network, and simple, deep, and powerful. Proceeding towards my next slide, the VGG16 model is a convolutional neural network. Like now we are going through the basics of VGG16. Who proposed that for the first time? That was proposed by the Visual Geometry Group. That is the full form of VGG, Visual Geometry Group. Sir, I've already mentioned earlier what is the full form of VGG, that is Visual Geometry Group. And it was first proposed by them at University of Oxford in the year 2014. So the paper name was Very Deep Convolutional Neural Network for large scale image recognition. I have already mentioned it in the references, so you can visit there in the reference part. So it is there in 2014. This paper was first proposed by them. So this is the overall architecture of VGG16. Like first, this is an abnormal or normal. This is a cancerous cell. This is the image I have taken here is a cancerous cell. So here the image height, here 224 represents the image height and this 224 represents the image width, and 3 is the RGB color channels. So while passing the image as an input to the convolutional neural network architecture, here these 2 convolution block, it represents already, I have mentioned which block represents what. Here convolution and these blocks, and then here we'll be performing max pooling. What are the operations I have explained elaborately on the further slides. So first there are 2 blocks of convolution and then max pooling happens. So what is the work of max pooling and how convolution happens? I have elaborately explained the mathematics in the further slides, and how the width, image height width reduces, and generally 64 is the number of filters. So how 64 increased to 128 and 256, I will be explaining all over that. So convolution, and what is ReLU function, how that works, what is max pooling, and I'll be explaining all over that. So convolution 1 has 64 number of filters, that is, these are the number of filters. So I have considered convolution 1 and convolution 2. I mean both, taking both, I have considered this is a single block of convolution 1, and convolution 2 has 128 filters. Convolution 3 has 256 filters, as well as convolution 4 and 5 have 512 filters. So this is the architecture. Um, yeah, VGG16 architecture. What does the 16 in VGG16 refers? So it refers to 16 layers that have weights. Here, just count the number of layers here, 1, 2, and we'll be not considering the pooling layers because I have also explained this part. In VGG16, there are 13 convolution layers, as you can see here. You can count the number of convolution layers that sums up to 13, and 5 max pooling layers and 3 dense layers. The dense layers are also known as fully connected layers, so which helps in decision making. What is the work of dense layer? Mainly, it helps in decision making that the object belongs to which class. While passing an image, that is a particular object in the image belongs to which class, that is mainly determined by the dense layer. Which I mean, if we add all the layers, then it sums up to 21 layers. But why it is called 16 then? It is only 16 weight layers. That is learnable parameters layer. Something that the neural network adjusts during training to minimize the loss function. The non-learnable layers are pooling and the dense layers. That is, it doesn't consider any weights, and the weights are not increased or multiplied during the operation. So they are called non-learnable parameters or non-learnable layers, like pooling. Don't have any weights or biases. They only perform fixed operations, so they are not considered as any learnable parameter. Here, 5 max pooling layer just reduces the spatial size. What is the work of max pooling? Just it reduces the spatial size of the image. As I have already explained while while going through the convolution architecture, that is VJ16 architecture, the image size reduces. How it reduces? Because of pooling operation, it takes the maximum value. I will be explaining that on next slide. 5 max pooling layer just reduces the spatial size, which refers to physical dimensions or extent of an object or phenomenon, including its length, area, or volume. The convolution and max pool layers are consistently arranged throughout the whole architecture. That is, convolution layer and max pool layer are arranged through the whole architecture. VGG16 takes input tensor size as 224 cross 224 with 3 RGB channel. As in the previous slide, we already saw that how it takes the input image size, that is image height would be 224, image width should be 224, and with 3 RGB channel. If we look at the number of filters that we can use, around 64 filters are available that we can double up to 128 and then 256. So why do we double the filters? Just so that when the image size reduces, to particularly specify the texture, shape, and the region of interest, we generally increase the number of filters so it gives better output. In the last layer, we can use 512 filters. So proceeding towards next slide, VGG16 is also called a sequential CNN architecture because its layers are stacked one after another. Why VGG16 is all sequential? Since in my topic was that I'll be using a sequential convolution neural network. So why VGG16 is called a sequential CNN architecture? Because its layers are stacked one after another in a single linear chain, with each layer having one input and one output. Like you can see that I have added the previous image only here. Here each of the layers are stacked one after another in a linear chain, like linear way. You already know what is meaning of linear, like one after another. Here each layer have one input and one output. Like when I will be giving for convolution 1 1, there is one input, and the output from convolution 1 1 will be the input of convolution 1 2. That is, every layer has one output and one input. So linear stack of layers in a sequential model, the output of one layer becomes the direct input of next layer. Here the convolution, the output of one layer becomes the direct input of next layer. VGG16 follows this by arranging 13 convolution layers and 3 fully connected layers in a single line. Here, VG16 arranges it like there are 13 convolution layers which are arranged in a single line. Like there are not any extra multiple inputs or outputs. It's just like any input from this side and it goes through in a serial manner or like in a stack. So this is also called as going by sequence. So it is also known as sequential convolution neural network. No multiple inputs or outputs. This sequential arrangement means the model is not designed to handle multiple inputs or outputs simultaneously. That is, this sequential arrangement is not designed to handle multiple inputs. If you're giving multiple inputs, that it will give a this model is not designed for multiple inputs. So data moves forward in one path from start to finish, which is ideal for simple image classification tasks. For Simple image classification data just moves in one path, like going there comes one input and then it gives output, and the image input layers goes through this, and finally we get the output. That's why it is known as sequential convolutional neural network, because the whole architecture is just comes in a sequence, that is in a linear manner. So this is the diagrammatic representation of microscopic cell image classification on my AGMC2 dataset. So as I've already mentioned earlier, AGMC2 dataset is a binary classification dataset where it consists of only two classes, abnormal cancerous cells and normal cancerous cells. We'll be passing both, both these, here, this is the collection of AGMC2 dataset for binary classification, where inside it we'll be passing normal, these are the normal microscopic cells. As you can see, as you have already heard from previous lectures, that the nucleus, in maximum cases, and the nucleus remains small for normal for microscopic cells, so you can already identify that as normal classification, and for abnormal, the nucleus is much more larger. So you can already say that as normal, and these are some of the 4 images. Normally in AGMC2 dataset we have 50 images for both abnormal, and one for normal there are another 15 images. I've taken from 4 images from that just to show here. So we'll be training the model about normal and abnormal microscopic cell, and the input images. First of all, as you have already seen in the architecture, it takes the input images 224 cross 224 cross 3, and we'll be passing through the convolution layer, which is 224 cross 224 cross 64, and 64 is the number of filters, and it goes by, after that we will be doing max pooling. So I'll be explaining in details what is the max pooling doing here, what is the convolution, how it is reducing the number, the size, image size, the height and width, and what is the work of, here it is just an elaborate explanation of the architecture, which I have already previously explained, that how many convolution layers are there. Here you can see that, here you can, as we have already discussed, that there are 13 convolution layers. So you can count up to that 1, 2, 3, 4, 5, 6, 7, 8, up to 13 convolution layers are there, and 5 max pooling layers. And as you can see, the image height and width is also reducing one after another. So at last, after max pooling, 2D max pooling here, it gets flattened. That is, there is also a layer called flattening layer. And how this value came, that is multiplying the filters, this value comes, and then we'll be passing it through fully connected layer, where another name of fully connected layer are dense layers. So there are 3 dense layers that will be passing through. So, and what is the work of dropout layer? Dropout layer generally is used to reduce the risk of overfitting. Like, we can also skip for normal classification architecture, but VG16 is somehow is a larger model, like dropout layer is much needed, otherwise there is a chance of overfitting. So we have there dropout layer is also included, and after the fully connected layer, here one means that from the 2 binary classes it classifies a single image. So the target cell here, it has classified as abnormal microscopic cell. How it classified? That is the test image we will be giving in the code. If we take that as abnormal microscopic cell, then it classifies correctly as abnormal microscopic cell. While in the code, when we will be testing the image, while in the code will be, when we will be testing the image, giving the normal microscopic cell, then it also classifies as normal. So and I'll be showing the code that is I have used, so you can see that I have tested giving both normal and abnormal cancerous cells, and my model, that is VGG16, classified accurately. Proceeding towards my next slide. So this is just a normal data augmentation part which I have explained. Like, what is data augmentation? It is the process of increasing the amount and diversity of data. Like when do we do augmentation? When we have limited number of images in our data set and we need the model to learn more accurately and precisely, we just augment the data. That is, we do not collect new data. Rather, we transform the already present data. Like I have for here in AGMC2 dataset, we have limited number of images. For abnormal microscopic cell images, we have 50 images, and for normal, we have 50 images. So it is not enough for the model to learn what is actually the abnormal and normal cancerous cells. So here we will be performing augmentation. Like what are the operations that are performed in augmentation? There is rotation. This is just an original image of an abnormal microscopic cell, and if we perform rotation, this look like this. There is rotated image and shearing that looks like this sheared image, and zooming, cropping, flipping. These are some of the augmentation operations that we generally perform for our dataset to become like more for the model to train. We can increase the amount of images by doing augmentation, which is generally necessary, otherwise our model could not learn. Since the dataset, that is AGNC2 dataset, contained a limited number of images, so different augmentation operations were performed in both the datasets. That is, I will be using high-level dataset afterwards. So augmentation operations were performed in both datasets to increase the dataset size and enhance the model performance. So these are some of the augmentation techniques which I have performed in my code. So now, as I have already said, I have given an explanation of my convolution operation, how convolution operation works. So let us take an abnormal microscopic cell, and when we will be performing convolution over that, it is just a small portion of the image. If we take this patch and it consists of numeric values, as I have already considered an image earlier, where we can see from the cat there, when you enlarge this consists of numerous numeric values. So this is just like that. Let us consider a teeny patch from that image. Sorry, image is written over there. So I is a matrix which is 5 by 5 matrix and a 3 by 3 edge detection filter. This is a 3 by 3 edge detection filter to detect the edges, because in this type of cell the edge detection is necessary. So that detects edges. When we apply convolution filter to an image, the output feature maps height and width are determined by this formula. That is the W minus F plus 2P by S plus 1, where W is the input size. That is, what is the input size of this image? 5 by 5. And filter size is 3 by 3. Padding, here will be doing no padding, so it will be 0. And stride, since the how many pixels the filter moves each step, it will be 1, since the filter is moving one step at a time. So just putting all these values, the output size is 3 by 3. So the output is 3 by 3 for both width and height. I mean, for next slide, you can see here when I'll be multiplying the filter, that is convolution, doing on convolution operation over the 5 by 5 matrix with the filter, then it comes like multiplying the values 1 into 1 plus 2 into 0, and in this way I'll be getting the value minus 6. For output 1 1, it is minus 6. In similar way, for output 1 2, I mean moving each times the filter moves one step ahead, and in this way it moves 9 times to cover the whole 5 by 5 matrix. So because the output will be a 3 by 3 matrix, so it have to cover 9 times. Like if here the output for 2 1 is minus 6, 2 2 is 10, and 2 3 is 10. Proceeding towards next part, and output 3 1 is also minus 6, and 4 and 14. So output feature map would be like, I'm taking all the 9 values here and minus 6, 4, 14. So Here we can interpretation or the summary comes like that. The negative values, that is the am I audible? Okay.
Yes, yes.
Yes, audible.
Okay, sir. So I have performed a convolution operation. As I've said, the output here comes -6, and for output that is this place for this part, the output is 14 and 14. And collecting all the values all together in the next slide, the feature map comes like this. Just I've taken all the values. How this works is just normal multiplication, like 1 into 7 plus 0 into 8 plus minus 1 into 9 plus 1 into 1 plus 0 into 2 plus 3 into minus 1, and for 6 into 1, 7 into 0, and 8 into minus 1. In this way, we have performed convolution operation with the filter. That is the edge detection filter. So the output feature map looks like this, and the interpretation, that is summary, we can say that the negative values means the left edges are from, that is from the image till now after the convolution operation. Our model predicted it like that the left edges are dark to light, and high positive values means there is a strong edge. Since it here we have performed convolution operation with the edge detection filter, so the high positive values, that is the 14, here the highest positive value is 14, whereas the negative value is -6. -6 generally represent the edges from dark to light, and high positive values, that is there is a strong edge in the vertical direction, and this 3 by 3 filter is acting like a vertical edge detector, like a Sobel filter. So for next slide, I guess you have understood how convolution operation works. So we'll be proceeding towards ReLU activation function. What is ReLU? After convolution, we apply ReLU, that is rectified linear unit. It is generally used to remove the negative values, like this is the formula for ReLU, that is rectified linear unit. It just removes the negative values and to zero, that is converts the negative values to zero and keeps the positive value as it is. Here the output feature map that we have got from the previous slide is -6, 14, 14, -6, 10, 10, and -6, 4, 4. So converting after applying ReLU, we get the -6 get converted to 0. Here all the negative values converted to 0, or positive values are greater than 0. Like the negative values after applying ReLU just converted or gets positive, that is converted to 0, and the positive